Okay, so today I will show you some of the results we obtained during the last years on rare earth atoms adsorbed on graphene. This is a work I still conducted at Forschungszentrum Jülich in the group of Professor Stefan Blügel. And the talk will have a general focus on magnetic anisotropy. So the first question to answer is why we pick graphene as a 2D material for the adsorption of rare earth atoms. And there are several reasons to it. The first is that graphene is chemically simple, which means that in the interaction with the 4f atom, it will interact basically only via these perpendicularly oriented pi orbitals. So it's a quite simple interaction, and this is in contrast to other 2D materials which we also investigated, like transition metal dichalcogenides, where many orbital hybridizations were involved in the interaction, and of course, these have a huge impact on the magnetic anisotropy. Second, graphene represents a nice way to decouple effects, because, for example, it is not a source of spin-orbit coupling, which means that all the spin-orbit coupling effects, like magnetic anisotropy, would arise solely from the interaction of the 4f atom with the surrounding crystal field. And the crystal field in graphene is a kind of high symmetry crystal field, so C6V, which is also nice from the more practical point of view, because we will see that the higher the symmetry, the less the possibilities, the chances to have some effects that cause the stabilization of the magnetization, like quantum tunneling of magnetization. Lastly, graphene can be used as a decoupling layer from substrate. So we can, because it tends to interact with this kind of weak and long-range van der Waals interaction, so we can nicely decouple our magnetic heterostructure from a substrate. On top of graphene, we will put our rare earth atoms. Here you can see the lanthanide series. The main characteristic is the sequential filling of the 4f shell. So we will be dealing with highly localized F electrons, which give rise to large spin and orbital magnetic moments. And these are also kind of protected from the environment because of the high localization. And they give rise to strong spin-orbit coupling effects, and all these properties together, they basically represent the perfect playground in order to tailor large magnetic anisotropies, which is the fundamental property you want to have in the construction, for example, of hard magnets. So if we start with half-filled 4f shells, like europium and gadolinium, where we have 7 4f electrons, we have a vanishing angular momentum, which is reflected in a kind of spherical 4f charge cloud, which means that if you rotate this in space, it will more or less always interact in the same manner with the surrounding crystal field. So we do not expect large changes in the energy, which means that we do not expect large contributions to the magnetic anisotropy. On the other hand, if we go towards open 4f shells, we have some kind of geometry in space of the 4f charge cloud, which means that if we rotate the spin magnetic moment, for example, by 90 degrees, because of spin-orbit coupling, also this charge cloud will rotate and interact differently with the surrounding crystal field. So we can get these energy curves as a function of the magnetization angles, which gives some information on the energy barriers needed to rotate the magnetization and on the easy and hard axis of the magnetization. So in principle, the magnetic anisotropy relies on 2 main ingredients, which is on one hand, the shape of the charge cloud driven by the 4f orbital occupation, and on the other hand, the symmetry of the crystal field. And for an hexagonal crystal field, we can use this simple equation, which you can find in any textbook, where we have the k's, the keys that are the magnetic anisotropy constants, and then theta and phi, which are the polar and the azimuthal angle of the magnetization. So they are related to an out-of-plane and an in-plane magnetic anisotropy. So nevertheless, the classical picture I just gave is mostly not sufficient, and in order to have a complete overview of the magnetic stability, we need to go into the quantum framework and determine the splitting of the 2J+1 fold degenerate quantum multiplets. And this is because at the quantum level, some phenomena can happen which we cannot see classically. For example, quantum tunneling of magnetization, where the system can tunnel from one spin state to the opposite one without the need to overcome the whole energy barrier, but for example, via these states that can form at quenched expectation value, which are called tunnel split doublets. So if these tunnel split doublets are the ground state, quantum tunneling can happen directly. If they are not, like in this figure, it can nevertheless be activated via some excitation processes, for example. So it is always very important to understand how the 4f energy spectrum is split. And in general, we can write the crystal field Hamiltonian as a linear combination of Stevens operators multiplied by the so-called crystal field parameters, where you can see that the Stevens operators, they act on the multiplets, and they induce some kind of energy dispersion based on the numerical value of the crystal field parameters. So, for example, here you can see the action of the C20, the first, which is inducing a parabolic dispersion of the quantum multiplets. While if I introduce higher order terms, like the 4-0 and the 6-0, we also get a higher anisotropic behavior in space. So nevertheless, in order to consider the full hexagonal symmetry of the crystal field, we need to take into account this last term, whose effect is to mix states that differ by ±6 or 12 in the case of an hexagonal crystal field. And as you can see here, in these two situations, I modeled a half integer and an integer spin system. Now we have basically the formation of states in the same color, which are quantum superpositions or mixtures of states that differ by ±6. And in the case of the integer spin system, this causes the formation of these Tanner split doublets. So in principle, here we can have quantum tunneling of magnetization. So nevertheless, okay, here in the half integer spin system, these cannot form in this situation because of Kramer's degeneracy. But this does not mean that we never see quantum tunneling of magnetization in half integer spin systems, as it can also be induced by some external perturbations, as we will see also later. But from this, it is clear what I said at the beginning, that the higher the symmetry, the less the chances for this quantum tunneling of magnetization. Because if we imagine to reduce the symmetry to a trigonal, for example, we would have additional terms here in the linear combination that mix also states different, for example, by ±3, which means that we have more possibility of forming these Tanner split doublets, and this means also more chances to have quantum tunneling of magnetization. So from the experimental point of view, there are several studies on this topic. This is one of the most pioneering ones. And basically here they investigated single holmium atoms on magnesium oxide, and they found that the holmium adsorbs on top of the oxygen, which leads to a C4V crystal field and this specific orbital occupation of the foil shell. And the combination of these two ingredients leads to a magnetic bistability, hysteresis, protection against quantum tunneling of magnetization, and from the more practical point of view, quite large relaxation times of the magnetization. So now we head towards our simulations on this supercell of graphene. Everything was done using the DFT+U method as implemented in the FLIR code, which is a full potential linearized plane wave method. And there are basically three possible adsorption sites for our rare atom. So the hexagonal side, the top side on top of a carbon atom, and in between of two carbon atoms. And for all the rare atoms I investigated, all of them, they prefer always the hollow side. And this can be discussed based on the charge delocalization we can see also here, which is also related to the number of nearest neighbors. And so here you can see the rare atoms I picked. We have two representatives of half-filled 4s shells, europium and gadolinium, and then three open 4s shells, dysprosium, holmium, and thulium, which have strong spin-orbit coupling effects. And for these, I calculated these ground state properties, where we can see some correlations, for example, between the d-occupation and the adsorption energy, which is largest for gadolinium, because gadolinium already in its atomic limit has a full outer 5d electron, while all the other rare atoms, they acquire some d-occupation in the formation of this heterostructure. Then we can see very large spin magnetic moments of the rare atom, which gives rise to most of the contribution to the total spin magnetic moment of the heterostructure. And you can see that this is always a little bit larger, because we have also to consider some intra- and interatomic spin polarization driven by the 4f magnetic moment towards other delocalized electrons in the system. Lastly, considering the open 4s shell by having a look at the spin and orbital magnetic moments and the f occupation, in this case, we are considering Hund's rules. So here you can see the spin polarized density of states. In red, you can see the f peaks, and in blue, the rather delocalized d states, which are a little bit spin polarized. And overall, the system is metallic, so there's some n-doping from the rare atom towards the graphene monolayer, and this can be seen by the shift of the Dirac point towards lower energies. And there's an induced spin polarization into the graphene monolayer with an intensity that depends on the magnetic moment of the rare atom. So heading now towards the magnetic anisotropy, we start with the half-filled 4s shell. We can first see that the behavior is kind of a low-order magnetic anisotropy. So now in blue, you can see the total energy calculations with DFT+U, and in red, the fitting with this equation. Europium has an overall in-plane EZ axis with an energy barrier of 0.06 milli-electron volts, while gadolinium has an out-of-plane EZ axis with 1 order of magnitude larger magnetic anisotropy, and this is driven by this contribution coming from the 5d electron also. If you go towards open 4s shells, we can see a different situation. Now we have a highly anisotropic behavior in space, and also the energy scale is quite larger. So we can reach several milli-electron volts of magnetic anisotropy, which is quite nice if we consider that, as I said at the beginning, graphene is not a source of spin-orbit coupling. And here on the right, we have also the in-plane magnetic anisotropy, so with varying phi, where you can see that energies repeat every 60 degrees, so it reflects the hexagonal symmetry. But overall, in terms of magnitude, the in-plane contribution is always smaller compared to the out-of-plane one. So here's just another point of view, the three-dimensional magnetic anisotropy surfaces and the absolute minima. So we find in-plane EZ axis for dysprosium on graphene and some kind of canted EZ axis for holmium and thulium on graphene. So at this point, we said at the beginning that it's important to go to the quantum picture. So the idea is to go from the classical framework in terms of magnetic anisotropy constants towards the quantum picture in terms of crystal field parameters via what we called reverse engineering, where we basically expand in a point charge model our crystal field potential for F charge density in spherical harmonics, and we take an expectation value in a first order perturbational manner. And this leads to a direct relationship between the crystal field energy and these B's, which are basically the crystal field parameters just expressed in another convention. This is called the Weybourne convention, but we convert it into this Stevens convention. And the two are related just by some numerical factors that depend on the specific rare earth atom. Then we have these D's, which are related to the Legendre polynomials, which means that we can expand everything for an hexagonal symmetry and equate this to the classical formulation I showed before. And this leads to an expansion of the magnetic anisotropy constant as linear combinations of the crystal field parameters. So basically, here's the workflow. I did my DFT+U calculations, total energy calculations, which are then fitted to give the magnetic anisotropy constants. These are then reverse engineered into crystal field parameters. And with these, I could set up my crystal field Hamiltonian matrix, which is then diagonalized to give my quantum multiplets. And we can see that, well, in the dysprosium case, we have an in-plane axis. In the holmium and thulium, we have some canted ground state. And you can see that in the case of the integer spin system, we have the formation of these tunnel split doublets, but we find a single magnetic ground state here in plane. But in the case of holmium and thulium, we have a magnetic bistability. And in principle, without any external perturbation, the system has to overcome this whole energy barrier in order to show magnetization reversal. But what can happen is, for example, because of scattering events with phonons or conduction electrons, the system could be excited towards the first available state, from which then assisted quantum tunnel of magnetization can happen. So also in the half-integer spin systems, it's important to have a look at this quantum multiplets. Lastly, I want to show also that we can tailor a little bit this magnetic anisotropy via some external mechanical deformation. So here I simulated an external perpendicularly applied strain. So now in red, you can see a stretched situation, and in blue, a compressed situation. And we can see that it has an impact on the magnetic anisotropy. And specifically, the more the atom is compressed towards the graphene, the larger the energy barriers for rotation of the magnetization. And this is reflected also in the trend of the magnetic anisotropy constant. And if we have a look at the energy difference between an in-plane and out-of-plane magnetized sample, always in a certain range of strains, we can see that in some instances, there can also be a transition towards a different magnetic ground state, as seen here in gray for dysprosium, where the system goes from an in-plane EZ axis for a stretch situation towards an out-of-plane EZ axis in the compressed situation. And as also expected, europium and gadolinium do not show any magnetoelastic coupling, but gadolinium has a little bit more of magnetic anisotropy compared to europium. So lastly, I just want to give a very tiny insight on the fact that we also went a little bit farther and analyzed other 2D materials, which are chemically a little bit more complex compared to graphene, like tungsten diselenide, monolayer. Again, I picked europium and gadolinium as half-filled 4s shell representatives and holmium as an open 4s shell representative with strong spin-orbit coupling. And I investigated these two situations. One, we have a complete monolayer of the magnetic atom. And on the other hand, we have a more diluted situation of this magnetic source. And we wanted to understand how the different chemical behavior of the rare earth atom, considering that gadolinium has this outer 5d electron, and the impact of the coverage density is on the magnetic anisotropy. What we found is that for europium, we get a larger magnetic anisotropy in the full coverage situation, while it is quite smaller in the diluted situation. And here we basically have two contributions to the magnetic anisotropy. On one hand, a direct one between the 4f electrons and the chemical environment, and on the other hand, a more indirect one, which is due to the spin polarization coming from the 4f magnetic moment towards other delocalized electrons, and because of the spin-orbit coupling of the tungsten, we can have magnetic anisotropy. So you can understand that if we dilute the magnetic atom, we are diluting also the magnetic source and the magnetic source per spin-orbit coupling source, which here is the tungsten. So the effect of the magnetic anisotropy is reduced. Interestingly, in the case of gadolinium, we find the opposite behavior. So we have a smaller magnetic anisotropy in the full coverage density, and a larger magnetic anisotropy when it's diluted. And this is due to a different chemical behavior of gadolinium, because first of all, here we don't have the direct interaction, as we found that the 4s states are too far in energy compared to any other states in the system. And so everything is driven by the spin polarized d states that we see at the Fermi energy. And the fact that if we dilute the gadolinium atom, it gets much closer towards the tungsten diselenide compared to the magnetic monolayer case. So there's a strong interaction with the crystal field. If we have a look at holmium, which chemically behaves similarly to europium, we don't have the outside 5d electron. We have the same trend. So a larger magnetic anisotropy in the full coverage situation and a smaller magnetic anisotropy when it's diluted. And well, overall, of course, these magnetic anisotropies are much larger compared to the half-filled 4f shells because, I mean, it's an open 4f shell with strong spin-orbit coupling. We also have kind of to consider the fact that these open 4f shells contribute to the crystal field. So there's kind of like a 4f repulsion, which is much smaller in gadolinium and europium. And yeah, with this, I conclude by saying that in general, rare earth atoms on 2D materials are promising candidates at single atom magnets because of this interplay between the large spin and orbital magnetic moments. And especially in open 4s shells, already in a chemically simple material like graphene, we can reach several milli-electron volts of magnetic anisotropy. I showed a way to compute crystal field parameters, at least in the easy case of graphene, from ab initio calculations. And I mean, the key message here is not really the method, but the fact that we have to go into the quantum framework in order to have a complete overview of the magnetic stability. We can tailor a little bit this magnetic anisotropy via some mechanical deformation, and in some cases, this can also cause a transition towards a different magnetic ground state. And there's a variety of other 2D materials that we can still investigate for the adsorption of rare earth atoms. As we saw, by properly choosing these two ingredients and playing around with orbital hybridizations, we can reach quite large magnetic anisotropies, also in the case for half-filled 4f shells. And with this, I conclude. These are my collaborators at Forschungszentrum Jülich, not all of them, but some of them. And these are some people I discussed with during the past years, especially on experimental points of view on the topic.